for the first time in history, we get an image of one, and it looks like the prediction. So It's a remarkable thing.
How phenomenal is that?
Yeah. So we've had those 2 photographs. The other thing we've had is so-called gravitational wave detections. So these are colliding black holes, and they collide and merge together.
In 2019, humanity glimpsed the unseeable, the first image of a black hole. That blurry orange ring stunned the world, not for its clarity, but for what it represented, a shadow cast by gravity itself. But now, just a few years later, we've crossed another frontier. What you're about to see is not just an enhanced photo, it's a radically new window into the physics of black holes. Thanks to breakthroughs in quantum computing and artificial intelligence, scientists have processed black hole data in ways that were literally impossible a decade ago. And the results? They've left experts at the world's top observatories speechless. Today, we're diving into how quantum computing has transformed our understanding of black holes. The original 2019 image, captured by the Event Horizon Telescope, or EHT, was already a monumental achievement. It combined over 5 petabytes of data from radio telescopes scattered across the planet. That's 5 million gigabytes, all stitched together to create one image. But despite the power of those classical computers, much of that data was left on the cutting room floor. It was simply too complex, too noisy, too chaotic to process with traditional methods. That's where quantum AI enters the picture. Unlike classical computers that process one possibility at a time using binary bits, quantum computers use qubits, units of information that exist in multiple states simultaneously. This allows them to explore millions of possible solutions all at once. Imagine trying to solve a jigsaw puzzle where every piece can test fit with every other simultaneously. That's the power of quantum processing. When scientists applied quantum algorithms to the original black hole data, they discovered faint signals that had been completely buried in noise. The result? A dramatically sharper, more detailed image of the event horizon and the space around it. Here's the original 2019 image. Now, here's the quantum-enhanced version. The difference is striking. Look closely at the accretion disk, the bright ring of matter spiraling around the black hole. You can now see subtle asymmetries, temperature variations, even structures that suggest changes in density and magnetic activity. There's evidence of relativistic beaming, where matter moving toward us at near light speed appears brighter due to Einstein's theory of special relativity. And for the first time ever, we may be seeing hints of the polar jets, high-speed streams of particles ejected perpendicular to the disk at nearly the speed of light. But what quantum AI uncovered next is even more mind-blowing. The enhanced data revealed a ring of polarized light encircling the black hole's shadow. This ring appears at the so-called photon sphere, where gravity is so intense that light orbits the black hole multiple times before escaping, or not. Even more astonishing, the polarization isn't symmetrical. These subtle shifts suggest that the black hole in question, M87 star, is spinning faster than previously estimated, possibly near the theoretical limit. This ultra-fast spin leads to a phenomenon called frame dragging, where space-time itself is twisted into a vortex. Einstein predicted it. Now, we may be seeing direct evidence. These findings are shaking up foundational theories in black hole physics. The standard model of accretion disk formation, the mechanisms that power relativistic jets, even aspects of the famous no-hair theorem, all are now being re-examined. The data suggests more complexity at the event horizon than anyone expected. And then there's the inner shadow region, previously believed to be completely dark. The quantum AI has revealed faint emission patterns inside it, possibly linked to magnetic reconnection events. That's when twisted magnetic field lines snap and release immense energy, like solar flares, but on cosmic steroids. To understand how these breakthroughs were possible, let's break down the technology. The EHT is not a single telescope. It's a network of observatories across the globe working together through a method called very long baseline interferometry. By precisely synchronizing their observations using atomic clocks, they simulate a telescope the size of Earth. Each telescope collected massive amounts of data, physically stored on hard drives and shipped to supercomputing centers. Classical computers stitched the data into images using algorithms that had to make educated guesses and assumptions. They filtered out noise, interpolated missing information, and erred on the side of caution to avoid false positives. Quantum AI flips that script. These new algorithms don't discard noise, they dive into it. They search for hidden correlations buried so deep that classical methods can't find them. Quantum systems can explore exponentially more possibilities in a fraction of the time. What made this possible was a breakthrough in quantum error correction. Quantum systems are incredibly sensitive. Just a stray magnetic field or temperature fluctuation can collapse their quantum state. But new protocols using multiple qubits to stabilize logical operations have made it possible to run complex simulations long enough to extract meaningful results. In this case, it meant we could finally detect extremely faint polarization signals and track subtle magnetic field structures near the event horizon. One of the most exciting frontiers? The black hole information paradox. This is the unsolved mystery of whether information that falls into a black hole is lost forever. A contradiction with quantum mechanics. Quantum-enhanced imaging may allow scientists to detect subtle echoes of infalling matter, which could hint at how information is preserved or transformed. It's the kind of breakthrough that could redefine our understanding of reality itself. But the implications don't stop at black holes. The same quantum techniques are being adapted across astrophysics. Observatories studying galactic evolution, fast radio bursts, even the cosmic microwave background are now collecting data compatible with quantum processing. Tasks that would have taken classical supercomputers centuries are now being completed in weeks. A new observation run using quantum-optimized data collection is already scheduled to focus on Sagittarius A*, the supermassive black hole at the heart of our own galaxy. And it doesn't stop there. Researchers envision a future where real-time quantum processing gives us a constantly updating picture of the universe. A kind of quantum observatory that doesn't just watch the cosmos, it understands it. So, let's recap what quantum AI has revealed. Fine-grained magnetic structures near the event horizon, polarized light rings at the photon sphere, asymmetries in polarization suggesting extreme black hole spin, evidence of frame dragging and magnetic reconnection, challenges to long-standing black hole theories. We're witnessing the merger of two of humanity's most advanced technologies, quantum computing and high-resolution astrophysics. Together, they're allowing us to see the unseeable, decode the undecodable, and question the fundamental laws of nature. Black holes were once thought of as dead ends in the universe. Now, they're becoming gateways to new physics. If you found this glimpse into the secrets of black holes fascinating, make sure to subscribe and turn on notifications. Our next episode explores how the same quantum AI techniques are being used to detect biosignatures on distant exoplanets. That's right. The technology revealing the edge of spacetime is now being turned toward the search for life. Don't miss it.